In the last two sections, we've been measuring the mean of the sample and making an inference about the mean of the population. Now we're going to shift that a little bit. The equations change just slightly, but the intuition is very similar. We're going to be looking at sample distributions of a proportion. A proportion is some fraction of a whole. So these proportions are typically used for dichotomous variables where we want to know what fraction is 1 and what fraction is 0. We use the following equations, which I'll use in this example problem. What we typically find in a business program is that there are an abnormal number of males to females. So let's assume that our class was randomly drawn from the general population. Now we know that that isn't true. There's a self-selection where males tend to move to business programs more than females do. And you could find other programs that the opposite is true. But in this case, in business programs, you typically get a higher percentage of males. So we assume that the population proportion is 0.5 or 50%. So half males, half females. And that's pretty much what we see. Let's say that our sample size is 88. What is the probability that we'd have a class proportion of 0.284, so 28.4% women or fewer? And that's very similar to the proportion of women to men in business programs. Now, the first thing we need to do is make sure this fits the central limit theorem. So we look at our sample size of 88 times our expected proportion of 0.5, and we get that that's 44, and then 1 minus 0.5 times 88 is also 44. In both cases, it's greater than 5, so we can use the normal approximation method. We calculate our z-score, and the z-score in this case is from this equation here. So let's going to put that up here. So the z-score would be our sample proportion, which is 0.284, minus our expected proportion, which is 0.5, and then we need to divide by the standard error of the proportion. And this is where proportion calculations are a little bit different. So to calculate the standard error of the proportion, we take the square root of the expected or population mean, which is 0.5, times 1 minus the population mean, population proportion, which is 1 minus 0.5, so that would be 0.25, divided by our sample size. So we can see once again that our sample size is related to our sample distribution. So this calculation creates a z-score of negative 4.052. Now 4.052 is quite a few standard deviations away from the mean, and using a normal distribution we can use either the table or the norm dist function that we used before. We find that the probability of that happening, the probability of only getting 28% women when you drew them from a population that was half women, half men, is 0.000025, much less than 1%. So it's highly unlikely that this would have a sample proportion as smaller than 28%. Well, let's assume that the population that we're drawing from are not equally split between men and women. And in fact, this is more often the case that MBA programs and business programs in general have a pool of applicants that's about 35% women rather than 50% women. So now we want to know what's the probability of getting 28% women when we expected 35% women. So we can calculate the z-score like we did above, which would be 0.284 minus, this time, 0.35 divided by the standard error of the proportion, which once again is 0.5 times 0.35, times 1 minus 0.35 divided by our sample size of 88, and we get a z-score this time of negative 1.3. Taking that to a normal distribution table, we find that the probability of that happening now is just under 10%. So it's much more likely that we would have a sample proportion as small or smaller than 28% women if the population that we're drawing from is more closely, the proportional split is 0.35 or 35% women.